Hi everybody, this is Jim Corkins, and we're continuing on with our 10th and second to the final video in this series in one-dimensional kinematics. Again, please start reading the textbook. The chapters should be referenced in Canvas. Now, this video is all about y-direction motion, specifically in free fall. And we are going to do some application problems just like we did last time, practicing that procedure that I was teaching you. And so, free fall is a specific type of motion where there is no air friction, right? So it's kind of difficult for us to imagine that, especially since we do not have any, well, most of us don't have any typical experiences where we are falling or something is falling in a situation where it's in a vacuum, okay? So here's a couple things to put in mind, okay? So I'm going to go to the internet. In our everyday experience, we are more in a situation where we are in air. Which air is a viscous fluid, okay? So you know how when you drop like a rock in a pool and you see the rock speeding up and then it kind of hits this floating and it's slowing, it's not falling as fast as it does in air. Well, imagine yourself, we are in a very similar situation. We are in a viscous fluid, which is air. It's a compressible fluid. So this is a perspective of us looking up at clouds that are nice and even. And if you notice, waves start to form. So imagine yourself as a fishy looking up at the ocean as waves are breaking. Notice this wave is breaking across the surface of the ocean. And of course, this video is sped up. But we are in a compressible fluid, which is air. So technically in air, you're sinking. You're not falling. I consider falling as in free fall, where you're moving down, you're falling down with no air friction to slow you down or change your motion. Okay? So, going back to this, again, we are in a viscous fluid. Looking up at the ocean, a very light viscous fluid, but it is a compressible fluid, okay? Is when, what free fall is when something is falling with no air friction. So with air friction, things fall, you know, of course, due to the gravity, but their density becomes important. But without air friction, their density is unimportant and the two objects will fall at the same rate. So we're about to watch a video where the astronaut is on the moon and the moon has no air. Things are falling slower because the gravity of the moon is 1/6 of the Earth. But you will see this feather and this hammer falling at the same rate. Okay? So let's go ahead and watch.
Copy to both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got the...
So in his right hand, our left side where my mouse is, this is a hammer. In his left hand, which is the right side of our screen, is a feather. And when he drops them both, you will see what it looks like when two objects fall without air friction. And this is called free fall.
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
So we just saw that two things that have vastly different masses, a feather and a hammer, which would be a coin and a feather, are dropping at the same rate in free fall conditions where there is no air friction. Okay? Now, in our book, we are going to use the gravity of the Earth, or the acceleration of the Earth, as 9.8 meters per second squared. Okay? Now, just so you know, this is an overall average of the Earth. Different parts of the Earth have different magnitudes of gravity. And again, gravity is an acceleration. So the reason why this is, well, the North Pole has a higher gravity than something close to the equator, is because when the Earth is spinning, it's not a perfect sphere. It's more oval. So things around the equator, here's the North Pole, and here's the South Pole. Well, if you're on the equator, you're actually further away from the center of the Earth than something right here on the North Pole or the South Pole. Okay? And the further away you are, the less gravitational pull the Earth has. Okay? And we'll get into the physics of that a little bit later on when we get into energy. But basically the gravitational pull of the Earth acceleration is going to be 9.8 meters per second down. Okay? Now, let's go ahead and talk about that. All right? So when you drop an object from rest, it begins, its initial velocity is 0. Okay? So it's initially not moving at all. So when we look at this, the initial velocity is 0. And we're just dropping the object from rest. So its initial velocity is 0. And its initial position is going to be some distance above this line. So right here, it's dropping from rest from a position of 0, and its velocity is 0. When you drop something, and you're dropping it from your body, and it's dropping, maybe you're on top of a building or something, and you drop something, your initial position in the y direction is 0. You are the center of the universe. Okay? So anything dropping below you is going to have a negative, these are all going to be negative values. They're going to be dropping down. Okay? And since its velocity vector is down, and we're considering down as the negative y direction and up as the positive y direction. Just like to the right is positive, to the left is negative. Well, up is positive, down is negative. Okay? So when you drop something and your initial position is 0, it is going to be falling below you at a high rate of speed. Okay? And it'll start picking up speed. Okay? So your initial velocity is 0. Well, gravity is going to be dropping, is going to be adding that negative 9.8 meters per second velocity for every second. So after the first second, you're going to be traveling at 9.8 meters per second, which I'm going to put that number in right here. So we'll just call it 10. And then now you're traveling at negative 9.8 meters per second. And now we're going to add another 9.81 meters per second for the next second, which now you're going to be going at 19.6, which is 2 of those velocities that gets added. So now you're traveling at about 20 meters per second downwards. Again, you're going to be adding a negative 9.8 meters per second acceleration to the negative 19.6 meters per second velocity, and now you'll have a new velocity of negative 29.4 meters per second. So at the third second, you're at negative 29.4. And then finally, it's going to have one more addition to that negative acceleration. So now you're traveling at negative 29.4. Well, this is going to be adding a negative 9.8 meters per second velocity over the next second. And now your new velocity is going to be negative 39.2. So you can see right here, in a velocity versus time graph, it's a nice straight line. Well, it should be a nice straight line. The slope of that line is a negative slope, which is gravity. Okay. Now, in the y direction, your displacement, which you could get a lot of ways. We're going to go ahead and you could calculate it here with 1/2 g, which is going to be a negative number. So we're going to have a negative g. We're multiplying by half. Delta t squared, which is going to be 1 second squared, plus your initial velocity in the y direction, which is 0, times delta t, which is another 1 second. So if we calculate what your initial position is after the first second, after you've dropped it, okay, pull up our calculator. We're going to have 1/2 times 9.8, that is negative, times 1, negative 4.9. So your initial position after you drop it, so if this is 10, your initial position is going to be about 5. And then after, so let's put this as negative 4.9 meters. So you've dropped in the first second negative 4.9 meters. Well, now, as you're dropping at a negative 19.6 after the second, you are now at about 20. And then after the third second, you're almost at 55. And so I'm going to take this as 50, 45. And then finally, at the fourth second, you're at almost 80. So take this across, negative 80. So you can see that this is a curved, you can see that this is curved. And this looks like an object in a position versus time graph in the y direction position is speeding up, okay, from rest. So its initial velocity at this point is 0. So the initial velocity in the y direction is 0. And the initial position in the y direction is equal to 0. And then in the end, its final velocity in the y direction is going to be as negative 39.2 meters per second. And its final position at this point is going to be negative 78.5 meters. And this should be meters per second. And so you could tell that that acceleration is changing negative 9.8 meters per second, is adding negative 9.8 for every second and increasing that slope and becoming it more increasingly negative. Okay, this is free fall, where something falls without any restriction due to air friction or any other kind of fluids, water, air friction in it, and it falls. Okay? Now, when you throw a ball up, there's some interesting things that are happening. Now, it's still accelerating straight down at every single point, okay? But its velocity vector is switching. So, when you throw a ball straight up with an initial velocity of 39.2 meters per second, its initial position is 0. So, you're going to be under the ball the entire time once it leaves your hand. So you throw a ball upwards. Now it's moving upwards as acceleration is pointing down at every single point in time. So I'll write these acceleration vectors over here. G. Negative G. G again is gravity, which is negative 9.8. Okay? Now, once it leaves here, your hand at 39.2 meters per second, gravity now is going to be subtracting from that initial velocity as it moves upwards for every 1 second. And then finally, it comes to a stop. Now, gravity is always pulling on this object downwards with the same amount. So even though it's not moving, it's still got an acceleration downwards. Okay, so it's really interesting that when you throw something up, it slows to a stop, and then now its velocity at the top is equal to 0. And then it's turning around and speeding back up as it's moving downwards. So what we could say about anything thrown in a gravitational field, when it reaches its maximum height, its velocity in the y direction, not necessarily the x direction, but its velocity in the y direction is 0 when it reaches its maximum height. So what you could say for sure as a fact, when something reaches its maximum height, where its velocity in the y direction is equal to 0, that its height is the maximum. Which in this case is 78.5 meters. And something else interesting happens. So now it took 4 seconds to reach its maximum height. Well, now it's going to take another 4 seconds to fall back down into your hand. And notice that the speed that you launched it up with, which is 39.2 meters per second, is the speed that is coming back down at. Just in the different direction, right? It's got a positive velocity, positive 39.2 meters per second up. It's got a negative 39.2 meters per second down. Okay? And so what you could also say too is if it started out at 0 seconds and it landed back in your hand at 8 seconds, it had to reach its maximum height in that half time of flight, which is 4 seconds in this case. And so what this looks like on a position versus time graph is this. So you're going to give it a little, so this is 5, and then so the first second is 5. The second second is about 20. Its position at the third second, it's about 44. And at the fourth second, it's at 78. let's try this again. This is 20. This is 44. This is 78. I think these are spaced out. I'm doing my best. And then it's going to go back to here. So let me plot this a different way. So starting from here, it's going to go up, reach its maximum height, and reach its maximum height, and then fall back down. Okay. Over here, you've given it 40 meters per second velocity, and when it reaches its maximum height, it's now got a velocity of 0. So notice the slopes of this. The slope here is the initial velocity of positive 39.2 meters per second. When it reaches its maximum height, the slope here is 0. And then when it's coming back down, it's going to be coming back down with the same speed. Terrible at drawing, but in a different direction, so downwards, the same speed. Okay, so in other words, it starts out with a positive 39.2 meters per second, slows to a stop where the velocity in the y direction is equal to 0, and then when it reaches its when it's landing back in your hands, it's falling down in your hands with the same speed that you sent it up with, which is 39.2 meters per second. And this slope at any given point in time that acceleration, which is the slope, is negative g, which is negative 9.8 meters per second squared. So anyways, if you notice, since it always has this acceleration at any given point in time, even though it's not moving, you can still see it has an acceleration right here, which means gravity pulls on everything equally down, no matter what your mass is, as we've seen with the feather and the hammer, with the same acceleration. It sets your acceleration to be pointing down at 9.8 meters per second squared. Okay? So since we're going to be dealing with things falling in a gravitational field, we got to set up some rules. We're always going to set your position as 0. So 0 is going to be you. Okay, so things above you has a positive position. Things below you have a negative position in the y direction. Any vectors pointed upwards are a positive velocity. Any vectors pointing downward, we're going to call a negative velocity in the y direction. And g, which is gravity, is always pointed downwards at 9.8 meters per second squared. And since we called down as negative, that is going to be, we're going to call that a negative number. So our motion equations are going to have to change now. They're going to change x direction stuff into y direction. So delta x is now delta y. Okay? And so, but other than that, we are following the same procedure that we just did in the last chapter. So again, this procedure hasn't changed. So let's go ahead and start working with and doing some problems, okay? Now, some of these tutorials, which we're going to do, we don't have to, again, you don't have to construct the motion diagram if you don't want to, but it does help, okay? So here's the procedure. The first part of the procedure is to write down the motion equations, write down the 5 variables. Then what we're going to do is we're going to read the question, and when we're reading the question, we're going to look for numbers, and we're going to try to look for information. So a physics student drops from rest her biology textbook. So that sounds like the initial velocity is going to be equal to, in the y direction, is going to be equal to 0 from the roof of a science building. The book strikes the ground after 2.5 seconds. So this is going to be time. So this is time. And it's telling us to ignore air resistance, so it's in free fall. Okay? And so that's what they're asking us. How tall in meters is the science building? Okay, let's look at that first question. How tall in meters is the science building? So they're asking us for how tall it is, which is a distance, rather a displacement. They've given us the time, 2.5 seconds it took. It dropped from rest, 0 meters per second. Now, at first appearance, it looks like they gave us only 2 numbers, which we can't solve for anything. We need 3 numbers to actually solve for something. Well, if it's falling under gravity, that's going to be negative 9.8, or rather 9.8 meters per second squared down. Okay? Okay. Just real quick, it's going to look a lot like that very first slide we did over there where it drops from rest. The initial velocity is 0. And then it starts to speed up as it falls. So this is going to be... let's... And finally hits the ground. So this is y is equal to... So it's going to be starting here at a height of y, because you're on top of the building and you're dropping a ball. Okay? So its velocity is 0 and it's dropping. So each one of these, 0 seconds, this is going to be 0.5 seconds, 1 second, 1.5 seconds, 2 seconds, and 2.5 seconds. So this kind of helps us see what's happening. So as it starts building up its velocity. And remember, after the first second, it needs to be traveling at 9.8 meters per second down. Since it started with a 0 velocity, you add this negative 9.8 meters per second for every second, so that after the first second, it's going to be traveling at 9.8 meters per second down. Okay, so once we understand the problem, we don't have final velocity. So any equation that has final velocity in it, we cannot use. So this has final velocity in it, this has final velocity in it, and this has final velocity in it. So the only equation we're going to use here is the first one, which is already set up for us. We don't have to do any algebra. And I'm putting directions to things in the y direction now. So this is the acceleration in the y direction. This is the initial velocity in the y direction. Okay, let's start plugging in our numbers. So it's displacement starting from 0 all the way down here. That is going to be delta y at the bottom. So hopefully that will work out to be a negative number because it's dropping below us. Gravity is 9.8 meters per second squared down. The time, which is going to be 2.5 seconds, we're going to square. Now the initial velocity is 0, so this is going to be basically plus 0. Right there. So delta y is going to be equal to, let's get our calculator out. And I don't know why I put the negative in front of this, because the 9.8 is negative, the half is not. So this is going to be 0.5 times 9.8, that is negative, times 2.5 times 2.5. That's 2.5 squared. So it's going to fall down negative 30.625 meters. I try not to round too much, or if I do round out to the fourth place. Negative 30.625 meters. All right. Well, now we know its displacement in the y direction. All right, I'm going to write that down here. Negative 30.625 meters. In the second part, they're asking how fast it was moving. What is its velocity right before hitting the ground? Okay, well, we could use any equation that has v final in it. So that gives us the last three equations we could use. The easiest one, as always, is the second one. So to find the final velocity, this is what we're going to do. Plus the initial velocity in the y direction. Just put a little y here. And now we're going to plug in our numbers, which this is going to be negative 9.8 meters per second squared down times 2.5 seconds plus 0 meters per second. So that final velocity in the y direction is going to be this. Let's see. 9.8 negative. Hopefully this works out to be a negative number. Times 2.5. Negative 24.5 meters per second. So it's traveling right before it hits the ground. It's got this as its speed. So here are our two answers. So again, that procedure works for every situation I've seen in kinematics. Okay? So when you release the ball from rest, it's just going to be speeding up as it's falling down. Okay? All right. And so this problem corresponds really closely to this first situation right here. Now, the second problem that we're going to do is going to be about a ball being thrown upwards. So we have to know some things about that. Actually, let's go take a look at the problem real quick. Thrown straight upwards with a speed of 5.85 meters per second. So we have to know some things. Again, we have to remember things that happen here. When you throw a ball upwards, it's slowing down as it's moving to its maximum height. And at its maximum height, its velocity is going to be 0. And now it's going to turn around and speed up as it's falling back downwards. And when you catch it in your hand, it's going to be traveling at the same speed downwards as it was traveling upwards. This whole time of flight, if you divide it by 2, that would be the time of flight, 1/2 the time of flight. Time of flight is when the ball reaches its maximum height, where its velocity is 0. So we have to remember these kind of concepts. Okay? And we'll talk about them as we go here. Okay? So again, start off, write your 4 equations, write your 5 variables in the y direction, since this is free fall. From the ground level, a ball is thrown straight upwards. So ground level meaning your position is 0 here, so you're standing on the ground. You're throwing a ball straight upwards at 5 meters per second. So positive 5 meters per second. Okay? Now it's going to it's going to come to rest at the top. So we know it's going to kind of get smaller and smaller and smaller and smaller until it finally comes to a stop. And so we know when it reaches its maximum height, its velocity in the y direction I'll just put its velocity here in the y direction is equal to 0. Okay, so you're throwing a ball straight upwards, and it reaches with speed of 5 meters per second, and it reaches its maximum height and comes to a stop. We want to know how long does it take for the ball to reach that height, so in the y direction. We know it's got initial velocity in the y direction as upwards as positive 5 meters per second. Its velocity in the y direction, its final velocity when it reaches that maximum height, is equal to 0. And we know, of course, since this is free fall, gravity is pulling down the whole time at negative 9.8 meters per second, even though at the top it's not moving. Okay. We don't have delta y at the moment, so we can't use this one, we can't use this one, and we can't use this one. So we have to use this equation to figure out the time it takes. Okay. Okay. Now I'm going to solve this for delta t. The final velocity is 0. So I'm going to subtract both sides. I'm going to subtract v initial y from both sides. When I do that, since this is 0, you're just going to have a negative v initial y on the other side, delta t. And then we're going to divide both sides by the acceleration due to gravity. So this is going to be equal to a negative, where the positive 5 meters per second square, 5 meters per second, divided by negative 9.8 meters per second squared. So the time it takes to reach its maximum height is going to be, it's about 2, but not quite. A little bit over that. I mean, a little bit over a half. So 0.510. So 0.51. So a half a second. All right. Now, for part B, they want to know how high it goes. So we're going to put our time in here, and we're going to switch that question mark to this. Our question mark is here, and 0.51 seconds. So now we want to know what delta y is, which is going to be how high it gets to. We want to use the easiest equation to work with. So that means we could use anything that has delta y in it. We've got this one, and this one. I happen to think this is the easiest equation to work with right here in this particular case. So we could work with this one, or this one. This last one, we'd have to do a little bit of algebra. This first one, you have a square in it. So I think this is the easiest to work with. Just my opinion. Especially since one of our velocities is 0. Initial velocity is positive 5 meters per second plus 0 meters per second, which is final velocity at its maximum height, times delta t, which is 2.5 seconds. So I just had this equation right here, and I just started plugging in the numbers. So this delta y is going to be equal to, let's use our calculator, 0.5 times 5 times 2.5, 6.25 meters. So in a half a second, it's going to rise up a distance, 6.25 meters. And that's how to do it. So that's the procedure. Again, it's not necessarily to do the motion diagram, but it does help me visualize what's happening, and it keeps me from getting in trouble. Okay? All right. Let's try a couple more problems. Okay? And these are very similar to your homework. Okay. So reading this problem is, again, a lot like when you throw a ball upwards, that situation where it throws the ball upwards. But unlike the last problem, it's going to be coming back down into your hands. Okay, I think that's what they're trying to say here. So again, start off, write your equations. That'll help you memorize the equations, and write your 5 variables here. Now, a physics student shoots a ball vertically into the air. It's going to land back in your hand. So you throw it up in the air, and it's going to be landing back in your hand. So even though it is changing direction, the acceleration is down the whole time. So we don't really need to do a lot of fancy math, and delta probably don't need to do these variables twice like we did in the last time when we had somebody speeding up and then slowing down, and they had 2 different accelerations. If they have the same acceleration the whole time, likely you won't have to do this procedure twice. Anyways, so he shoots the ball vertically upwards into the air, so that's the initial velocity upwards. And we want to know what its final speed is going to be landing back in the hand. So that's going to be the final velocity when it's coming back down. The initial velocity is upwards at 20 meters per second. I don't know why I wrote that. We know gravity is 9.8 meters per second squared. Now, we only have 2 numbers, this and gravity. So right now we can't solve it. We absolutely don't know the time. The delta y is kind of interesting, because when you shoot a ball, you're down here, your initial position is here. It's going to rise to its maximum height. So shooting it up at positive 20 meters per second, it's going to rise to its maximum height. And then right here, it comes to a stop. So it comes to a stop at its maximum height, and its velocity in the y direction at this instant is 0. But then it's going to come downwards, and it's going to be speeding back up to its original speed, but coming back downwards at 20 meters per second. Okay? And so its final position in the y direction is equal to its initial position in the y direction. The interesting thing is, if this is the initial velocity when it's leaving your hand, this has to be the final velocity when it's landing back in your hand. It has to be. I think they're asking us to prove it. So in order to prove this, we know the answer is going to be negative 20 meters per second. But we also know your change in position from beginning to end is 0. So let's prove that final velocity is equal to 0. Okay, we don't have delta t. Okay, and we need to find v final. So we don't have time, so this time this doesn't work, this doesn't work, and this doesn't work. Well, we have to use this guy. All right, v final y equals v initial y squared plus 2ay delta y. And we're going to have to square root both sides. So this is just going to be this, but square rooted. So the final velocity, well, now that we're square rooting it, is turning into a speed. So we're going to put in our numbers here. This is going to be 20 meters per second that we're going to square, plus 2 times a negative 9.8 meters per second squared times 0 meters. So our v final y, which is really weird, is just 20 meters per second that we've squared, and we square rooted. So it's going to be landing back in at the same speed that it left your hand, which is 20 meters per second. The velocity will be negative, but the problem is asking for its speed, so that speed is going to be 20. All right. Now they want to know what is the total time of flight from where it left until it landed back in your hand. So now we could do any one of these equations that has time in it. And you guessed it, we're going to use my favorite little guy right here, this guy, which is v final y equals a delta t plus v initial y. That's going to be, so we're going to subtract the initial velocity onto the other side, divide, and then divide both sides by the acceleration. When we do that, we're going to get this to get the time. So the final velocity in the y direction is going to be negative 20 meters per second minus the initial velocity, which is a positive 20 meters per second, divided by 9.8 meters per second squared. Basically, we have two 20s in there because it's for the time it takes to be launched up to the time it takes to fall back down. So that's the reason why you kind of have two 20s in there conceptually. So this speed is going to be right here, 20 as negative minus 20 divided by 9.8, which is negative. So 4.02. 4.082. 4.082 seconds. So that is the time of flight from going up to coming back down. And the last question, what is the maximum height that the ball has reached? Okay, well, if we want to find out its maximum height that the ball has reached, we do kind of have to do another set of variables. So what I'm going to do is I'm going to grab this right here. Hold on a second. So now that the nature of the problem has changed, so since the problem's nature has changed, we do have to do something different. Okay? So the initial velocity isn't going to change. That's still positive 20 meters per second. And gravity is not going to change because it's always 9.8 meters per second squared downwards. But they're asking us to find the maximum height that it gets to. Now, when you throw a ball upwards and it reaches its maximum height, we know the velocity in the y direction is 0. So we know it's going to get to a velocity in the y direction that is 0. And we could solve it right now, but we also know something else too. If the total time of flight is 4.082 seconds, then we know it reaches its maximum height at half that time, because that's one of the rules. Divided by 2. So 2.041. So we know a lot of information. 2.041 seconds. So now we just have to choose one of the equations that has delta y in it. And again, I'm going to choose the simple equation that I have to do the least amount of algebra. I'm going to try to reduce my errors, which is going to be v initial y plus v final y delta t. Okay, we could have done any of these, but I don't want to do too much algebra. So here we go. Let's go ahead and put in our numbers. 1/2. The initial velocity in the y direction is positive 20 meters per second. The final velocity in the y direction is 0 meters per second. And time is 2.041 seconds. All right. So that's going to be 0.5 times 20 plus 0, which is 20, times 2.041. 20.41. So it reaches, so its maximum height is 20.41 meters. Okay? So that's the maximum height. Again, the maximum height occurs at half the time of flight. When its velocity is equal to 0 at that height, it's still got gravity pulling down on it. Okay. Last problem, which again, I'm just trying to help you have reference points for all of your homework problems. This one is a really cool problem, okay? You're going to launch a ball thrown straight upwards with a speed of 20 meters per second. So it's going to start here at 0. You're going to launch it up at, again, positive 20 meters per second, which is the initial velocity in the y direction. It then rises to a stop, so it's rising upwards, and it comes to a stop. Now we know that is the maximum height, and we know velocity in the y direction is 0 at that point. Okay, and then it's going to start coming back down, so it's going to be turning around. So it's going to turn around and start falling back down, and then it's going to hit a branch 5 meters above the ground. So it's hitting a branch right here, and we'll call this y is equal to positive 5 meters. Positive because it's above you. Okay. And so how long did it take to go the entire trip from going up, coming to a stop, and then falling back down and hitting that branch? So that, how long did it take? That sounds like time. So we're going to put our question mark next to here. Okay. We know the initial velocity in the y direction is going to be positive 20 meters per second. We know gravity is negative 9.8 meters per second squared. And we know the displacement, because it's only going from here. Yes, it's coming all the way top and coming back down here, but its displacement goes from here to here, right? If you go 10 steps up and then 5 steps down, your displacement is going to be positive 5. Just like that, those vector addition and subtraction in one dimension. So the displacement is positive 5. We don't have final velocity. So any equation that has final velocity in it, we cannot use. Oh boy. Looks like we're going to have to use this as our equation. Okay. I think I know what's about to happen. And this is the blunt force way. I think we could do this problem a lot of ways, but we're going to just go for the blunt force where we put in all the numbers that we have, and let's figure out how to solve the problem. Okay, so we need to solve for time. We have the initial, we have the displacement in the y direction. It's one of the few times that I'm actually putting in numbers in the beginning. Delta t plus the initial velocity, which is 20 meters per second, delta t. Okay? And we need to solve for delta t. This, I recognize, if we subtract if we subtract 5 meters onto both sides, we get something that's going to look ominous. This is going to be 1/2 of negative 9.8 meters per second squared, delta t squared, plus 20 meters per second, delta t, minus 5 meters. Let's do something real quick. 9.8 meters per second squared divided by 2 is negative 4.9. So I'm just going to write negative 4.9 right here. This is this. Let's make it look a little bit more. So this part right here is this. Anyways, so we have negative 4.9 meters per second squared, delta t squared, plus 20 meters per second, delta t, minus 5. This is a quadratic. In this quadratic, we have, we're going to have a delta t squared plus b delta t, and this is actually going to be plus a negative c. All right, so a is going to be equal to negative 4.9, b is going to be equal to positive 20, we're not putting in the units, and c is equal to negative 5. Okay, so the quadratic equation, okay, is going to be for delta t, which is going to be negative b plus or minus b squared, square root of 4ac, square root of minus 4ac all over 2a. Okay, so this looks worse than it is. It's really not that bad. It's this weird plus or minus kind of messes stuff up. So this is going to be negative 20 plus or minus 20 squared minus 4 times a negative 4.9 times c, which is a negative number, which is negative 5, all over 2 times a negative 4.9. Okay, I think a lot of your calculators have this equation in it. We're going to get two solutions. Okay, so we're going to do the first solution where we put in our numbers. 20, actually let's do this. Negative, actually do 20 squared minus, and then I'm going to put in brackets 4 that is negative times 4.9 that is negative times 5 that is negative, in parentheses, equals, so this is 498, and we're going to square root that. 22.3159. So this is plus or minus 22.3159 in there. This is negative 20. And this is going to be divided by negative 9.8. Okay. So when we do this, we're going to get two solutions. We're going to subtract 20 from this. Okay, so hold on a second. I'm going to pull out the two solutions. So when I do put this in the calculator, you get two solutions. You get a positive solution and you get a negative solution. Here's what this means. When it was traveling upwards at time 2.36, it was passing that tree on its way upwards. It was passing the tree on its way upwards. So right at this time, this is 2.36 seconds. It comes up, comes to a stop. When it's coming back down here, now it's hitting the tree at 4.318 seconds. So those two solutions means it's passing the tree on the way up and then passing that 5 meter branch on the way up, and then on the way back down is passing that branch again. So the time it takes to fall up and come to a stop and then turn around and fall back down is 4.318 seconds. That's what they're asking us to figure out. Okay. And okay. Now again, just like the last problem, they changed the nature of the problem again. And they want to know what is the highest point it gets to. Let me make this smaller, which I'll do over here because we're going to need some of our numbers. Okay, so to figure out how high it gets up, again, the physics really hasn't changed. It's been launched at 20 meters per second. When it gets to its maximum height, this is 0 meters per second. At that maximum height, 9.8 meters per second squared. And we want to know how high it got to, but we don't know the period of time. So, to figure out how high it gets up, we can't use any equation that has time in it, which means we can't use this equation, or this equation, and we have to use that last equation. V final y squared equals V initial y squared plus 2a delta y. Scooch the screen over a little bit here. Okay, so we need to solve for delta y, and this is 0. So we're going to have to subtract both sides. We're going to have to subtract v initial y squared from both sides. So we're subtracting that. When we do that, v initial y squared plus 0 is just v initial y squared. That's negative. Now 2a is being multiplied. So we have to divide 2a onto both sides, or multiply through by 1 over 2a. And when we do that, we get 2a down here. And that's equal to delta y. So plugging in some numbers, we got negative 20. So the negative lies outside, and we're going to square this 20 meters per second on the top. We're going to multiply this by 2 times a negative 9.8 meters per second squared. And let's see what that is. So this is going to be 400 up top, and we're going to divide that by 2 times 9.8. The negatives cancel each other out. So that's going to be 20.41. So 20.41 meters. is how high the ball got to. Okay, that ends this lecture on free fall. It was a big lecture. We did get through a lot of problems that are very similar to your homework problems, and I wanted to help you out. I hope you have a good day, and please do the readings if you haven't started it. Thank you.